So our objective being the voice activity detection, and we want to improve the performance uh, in detecting the voice signal, okay, whenever there is the noise. Okay, right. So run the section, and so in this next part, so first we will read one audio sample, and we'll see how it's going to look like, and we'll try to detect the speech directly using a built-in command that is taken from the audio toolbox. Okay, audio toolbox, fine. So let's set the sampling rate as, say, sampling. Let's keep the sampling frequency is equal to 16,000 hertz. And now I want to collect the data from one of the file. Okay, so the file contains somebody talking. So I have the speech data, and also I want to read the sampling rate from the file, because the file might be recorded in a different what you call sampling rate. Okay, so I'll write this is file sampling rate. Okay, or sampling rate that is present in the file which we are reading. Okay, so audio read is the built-in command. This is directly taken from the audio toolbox. So first let me show you the help on this. Help. Audio read. So when I say when I specify the file name, it reads the audio present inside that file, and it also returns. This is these the y will be the it's going to be an array of all the samples, right? When I read a file generates a sequence of numbers corresponding to the audio that will come to y, and we have a sampling frequency related to each audio, right? That is fs. All right, so we can also specify from where to where. Okay, so start from this sample, go till this sample. If you have lakhs of sample, I don't want all of them, I want only specific, then I can do that. Okay, so many other options also do exist like this. So we have the support for .wav file, FLAC, mp3, mpeg4, etc., ogg, all these are supported. Okay, even we can read something from, right, a bucket location as well. Okay, so these are the options we have. So I'm going to use the same command to read this audio from a specific file that is present inside. So audio read. All right, so this is the file, and now I'll do the resampling. I don't want to have the sampling at the whatever is the sampling rate that is present over here, right? I don't want to get that. Okay, so let's see. Let's run this section, and you see the file sampling rate. You can see the file sampling rate is 44,100. That is actually considered as the CD quality of audio. Okay, then you have one more standard that is called as the DVD quality rate, which is 48,000, right? We don't want to have bigger or the larger number of data. So what I'll do in the next step, I'll try to do a resampling, in the sense convert the 44,100 into 16,000. it's called as a downsampling. Let's do that. Okay, so updated speech data. Okay, so yeah, speech data. Speech data is equal to, there is a function called resample. All right, so let's quickly look at what it is going to do. Help resample. So whatever data we have, that data will be converted into a new rate of data, right? We are uh, so if you have a higher sampling rate, you can convert into a lower sampling rate or lower to high, whatever we want, we can do that. So resample, right, will use this, right? X, P, and Q are the inputs. X is the samples, right? It will be sampled at P by Q times the original sampling rate, right? So that's what we are trying to use now. So let us use that to implement the resampling process. Okay, so resample, you see, according to the requirement, first is the data, right? What is the data? Data is a speech data. So you see, speech data is considered, comma. So now I need to say the value of P, that will be the sampling frequency which I want as a result. All right. So sampling frequency, this is the new sampling rate, and whatever is present, that will be the next one. The Q value will be what is the sampling rate of this particular, the current sampling rate of my speech data which I read from a file. So that will be file sampling rate. Okay, yes. So now this is done. Now let's try to run this section. Now you see, we will be having the speech data, right, whose number of samples are different than the previous one. Now actually what I can do is I'll show the difference. Okay, first let me comment this. I'll just run this part. Observe that how many speech samples we get. Okay, so look at the speech samples. The speech data, if I open, you see this is uh, 6,85,056 samples. Okay, that's the number of samples when I sample it at 44,100 at that rate. Okay, now I'll uncomment this and I'll run, so that I am downsampling this larger number, what you see here, will be reduced to a new value because I'm doing the downsampling, right? So sampling frequency is lower compared to the file sampling rate, so I get a new value which is lesser than this. So you see here now, correct? You see the number is just 2,48,547. Okay, so that tells that yes, because of this process we have reduced. All right, then there is one more process. This is called as the normalization. Okay, whatever speech data we have, I try to normalize that. So the speech data divided by I'll try to divide by its magnitude. Okay, highest value. So that is max of absolute, because positive or negative both are possible. So you can have max of absolute value of the speech data, right? This performs what is called as the normalization, right? Then, right, we can listen to that by uh, calling a function that is sound. Okay, so let's see the help on that first. Yeah, sound in the sense, whatever vector we have in y with a specified fs, it's going to play that as a sound. Okay, now you see for this there is a condition that value should be between +1 to -1. So outside that will be clipped. That's the reason why we did this, right? Speech is equal to speech data divided by maximum of absolute of that one. So absolute will convert negative into positive, then finds out what is the maximum value, then it will divide. Okay, so that's the one condition that is required to be satisfied. Okay, there are other options with the function. Anyway, we'll not use that as of now. So that can be ready to be required. So the speech data is what I want to play sound, and I want to play it with a specific frequency. So that will be the sampling frequency. Okay, so let me run this section now. So that runs, and now we can now I just want to use a function to see that what is the data, uh, at what locations I have, right, the what do you call, the speech in that. So I have one option here directly. I can try to plot it, plot of the speech data. Let's see, let me try to plot that and see what comes. Okay, the waveform we can see, right, but may not be very clear, but the top half is chopped even on my screen, not visible. Okay, I'll try to try that. One second, I'll try to bring it down so that we can see that clearly. I think we can see that, right? So this is the waveform, okay, of the one which we had got, right? Directly we try to plot it. We can see that wherever the voice is present, we have the signals, right? Others are not there. So you can see it's actually they are saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the data, right? When we play that, we can. All right, right. So that's the data, and it's very clear that okay, this is how it's going to look like. So in the our next option is that I want to use my okay, let's use one particular function that is actually present inside the audio toolbox. Okay, say I want to use the function detect speech, which is present inside the audio toolbox, to detect the speech directly. Right. So for that, what we want to have uh, a window. Okay, so window function is equal to one of the very famous window which we use in the audio or the speech processing is a Hamming window. So Hamming is a function. We have to specify what is the length, right? Length will be, so you see here, I'll try to use 50 uh, milliseconds. That's the length I want. So 50 e minus 3, 50 milli. It's into, I just have to multiply that with the sampling frequency. So that is the length, 16,000 multiplied by, and then you have options like I can use a option symmetric or periodic. Now I'll go for periodic. I want to create that with this option. Okay. So then we'll directly call the detect speech. Okay, so detect speech of, just tell where is that, right? It is in the speech data, and specify what is the sampling frequency, right? And I'll specify the window. The window equals to the one which we have defined now. So that is window function. Okay, so let's try to run this section now. So the speech is processed now, and after processing, we will get this view. So we can see that the detected speech has been plotted over here around the speech, right? Wherever we have the speech, right, we can see that, right, the blue colored boundaries have been plotted. Whatever is existing between the blue regions, right, we can say that is the speech. Okay, so here the speech was very clearly separated from others, in the sense the background, right? This is because in the background we don't have a lot of noise. It's a very clear audio. So in that, yes, right, directly it will the whenever we run this particular command detect speech, it will be able to detect the speech because of lesser amount of noise being present in the file. Okay, but now I'll try to modify. I'll take a different okay, so I'll take a different audio. So here we'll try to read a data which is a noisy data, comma. Once again, this is the sampling rate of the file. Okay, so file sampling rate is equal to the audio read Now I'm going to read a different file. Okay, that is this one. It's a washing machine noisy sound. And then again, this is at a higher sampling rate. I want to upgrade that. Okay, sorry, not upgrade. I want to downgrade, right? So that is at a higher sampling rate. I want to downsample. So the noisy data should be equal to, I want to go for the resampling option of the same data which we have just read, that is noisy data, comma, what is the requirement? The requirement will be the same sampling frequency. Okay, sampling frequency. And I want to, I have to specify what is the current sampling rate that will come from file sampling. All right, then let me first try to run this section. You can see that it is being read now. The noisy data is coming here, okay, in the command window. That's because I never give a semicolon at the end. That's why it is actually plotting. All right, let it get finished, then we'll go ahead. Okay, so that is done. Now we can see here the noisy data has these many samples. Okay, this is after doing the resamples. Okay, now we'll define the signal to noise ratio. This is required. Again, whatever we write, it is in the decibels. It's minus 20 dB. Okay, then we need to put the noise on our speech data. Okay, so that's why you see now what we have to slightly modify. We have to get what is called as a noise uh, gain value. The gain because of the noise is equal to, this is a standard equation. Okay, so the equation is 10 to the power, it's actually I'm trying to take an anti-log. Okay, anti-log is 10 to the power. If you remember, the if whenever we try to write in a decibel scale, we had taken a log over. Okay, 20 log to the base 10 of the SNR. That's what is a SNR in dB. Now in decibels we are calculating, we are considering the SNR to be 20. Okay, this is minus 20. I need to convert that into the normal number. From I have to take an anti-log. So how do you take anti-log? It is 10 to the power. All right, that whatever value you have, it's negative because minus 20 I have to make it positive. So minus of the SNR which we have defined now, I should divide this by 20 because normal equation is 20 log something. So there is a 20 multiplier I should divide. Okay, so that is one thing. Multiply this with the normalized value of the speech. You see, signal to noise ratio is what I'm trying to calculate. Okay, so this is into the norm. I'll show you what norm does. Right. So the vector and the norm matrix, whatever vector we have, its norm will come. So when I say norm of x, it returns a second norm of the x, right? So we can check the various types of norms here, right? One will be the Euclidean, one will be the highest singular value, etc. You can specify that if you need a type. Okay, as of now, I'm not using any type, I'm directly calling it. Okay, so that is the norm of the first thing. It's a signal to noise ratio. So signal is a speech data. Okay, norm of that divided by the norm of what's the other one? That's a noise data. Correct. So simply take the noise. So signal to noise ratio has been calculated. Now what I do, I create a new variable which is this speech data which is very clear, okay, which is very clear, very pure data. To that, what I do, I try to add this noise, whatever noise is coming from the washing machine. I'm trying to add that. Then I'll try to detect the speech in that. Okay, fine. So I calculated the gain value because of this. I'm supposed to add this. So noisy noisy speech data is obtained by the original speech data. To this you add plus the noise data. Okay, but the noise data, what I'll do here, I'll multiply by the noise gain because noise is getting added up. So I have to write the uh, noise gain value times multiply that with the noise data. Okay, noisy data, but you see their lengths are different. Can you see? Noisy data has these many samples, speech data has these many samples, right? So read only the length of speech data, whatever is the length, that length you read from that, remaining you can neglect. Okay, so noisy data of starting from 1, right, from the first sample, read all the values till the length of the speech data. How do you do that? So 1 2, it's a length of numerical length. Okay, numerical length of the speech data. Okay, and then I want to, let us say, we have not done the normalization because once again I need to do the normalization, right? So noisy speech data is once again equal to whatever we did earlier. I'm doing the same thing. Okay, so noisy speech data divided by maximum value of the absolute of the noisy speech data. Noisy speech data. All right, so let me try to run this part and see. Yeah, so we can see that yes, it's running. Okay, and at the end I'll try to go for a playing option, right? That is a sound of noisy speech data with the fs, the new value of fs. Okay, sampling frequency. So when we play like this, we will be able to hear the background noise, that is the washing machine sound, plus the original data, which actually somebody saying that 1 2 3 4 up to 10. Okay, so that's what we hear when we run that, right? Then now I'll directly go to try to detect the speech and see whether I'm able to see that. Okay, the same thing which I was able to see earlier, will I be able to get that? Okay, so that's my objective now. So let's add a section break, and I'll directly go for detect. So detect speech. From which data I want to detect speech? The noisy speech data. I also have to mention that which is my sampling frequency. Okay, sampling frequency, and I want to say that, okay, use the following window. Window is equal to, I think we gave a name as the same window I'll use. Okay, uh, window function. Window is equal to function. Okay, let me try to run this section. So the data what we see here, it's right, it's not detecting the speech like earlier. It's because of the fact that the fact is pretty simple. It's just because of there is too much noise. You see, right? It's actually not able to detect the speech separately, right? It says that first this much part is a complete speech, then there is a speech for a bigger duration. Actually, wherever you see the spikes like this, right? Only that is a speech data. Okay, here we have speech. Only this part is a speech. This is a speech. You see, it says that starting from here till here, it's the complete speech part. Okay, that's not true. We know that. Okay, so because of that reason, right, it's very clear that whenever there is a background noise, right, our built-in functions are not capable. Okay, we are not able to detect the speech, right, in the presence of what is called noise. So what we have to do is that we have to make sure that we will be able to detect the speech uh, in the presence of noise as well. Okay, so let's see how we can do that. Right? Okay, now in the next part of the code, our intention is that we want to build a